So the mean value theorem for derivatives states that if we have a function that is continuous on a closed interval and that it's differentiable on an open interval, okay, then there must be, and it's got to be the same interval, there must be at least one point somewhere between A and B, somewhere on that interval, where the slope of the tangent line is parallel to the slope of the secant line that goes through the endpoints of the interval. It sounds a little confusing. Okay. So I'm going to go through it again. If a function is continuous and differentiable on an interval, so continuous on the closed interval, differentiable on the open interval, then there is at least one point somewhere on that interval where the instantaneous rate of change, or where the derivative, is equal to the average rate of change, or the slope of the secant line. Does that sort of sound okay to people, or no?
Yeah.
Yeah? Okay, good.
Yeah.
Perfect. So the formula that we use for that is f prime of c, or the derivative, or the instantaneous rate of change at c, is equal to, and then that's just the slope formula, f of b minus f of a over b minus a. Okay. We're only guaranteed that this is true if the function is continuous and differentiable on that interval. Good? Good.
Yeah.
All right. So when we do the mean value theorem, I'm going to caution you to always make sure that both of the criteria of the hypothesis of that mean value theorem must be met, that it has to be continuous and it has to be differentiable on that interval. So if you look at something like the absolute value of x on the interval from -1 to 1, and here it is, absolute value of x from -1 to 1, is it continuous on the closed interval from -1 to 1?
Yes.
Yeah.
Okay. Is it differentiable on the open interval from -1 to 1?
No.
No,
Not
it's
completely.
Yeah, it's not differentiable. Yeah, for something to be differentiable on an interval, it means it has to be differentiable at every single point. So if there's just one point, and in this case, the point at x equals 0, where it's not differentiable, then we can say that the mean value theorem multiplied this function is not differentiable on the interval from -1 to 1. And so we can see that what's the average rate of change between the value at x equals -1 and the value at x equals 1 of this.
It's a horizontal line.
Right, it's just a horizontal line. So that should be 0, right? Yeah, the average rate of change of this function on that interval is 0. And clearly, if you look at that, nowhere along here is the derivative equal to 0, right? Because we know here the derivative doesn't exist. And all of these, it's 1, and all of these, it's -1. But f prime of c does not equal 0. Oh, that's a 1. I don't know why I wrote a 1 instead of a 0. F prime of c does not have to equal 0 because it's not differentiable. Now that doesn't mean that it might not. There might be a place on there where it did for some other function, but it's not guaranteed that it does. Okay? Or if we have something like the greatest integer function, you guys are familiar with the greatest integer function? Yeah, vaguely at least. And it looks like a step function. When I draw the picture, people will always go, "Oh yeah, I've seen that." Right? You guys are familiar with that one?
Yeah.
Yeah, so this one, mean value theorem doesn't apply because clearly it's not continuous, right? On any particular interval. Good. All right, so just make sure that the conditions are met. So let's take a look at f of x equals x squared and see if we can use the mean value theorem to find a solution C for this function. So first off, what should we do?
Do you test if the interval is continuous?
Right, so we're going to say that f is continuous on 0 to 2, and is it or no?
Yeah, it's a polynomial.
Right, yep. Yep, it's polynomial, so it must be continuous on all real numbers. And then what about f prime? F prime is equal to 2x, right? Right, does that exist? Does that always exist on the interval from 0 to 2?
Yeah.
Yeah.
And that's the open interval from 0 to 2. It also exists on the closed interval from 0 to 2, but that's beside the point. It exists on the open interval from 0 to 2, also because it's a polynomial. So we know that both of the conditions of the mean value theorem have met. So we know then we are guaranteed that there is a place where f prime of c is equal to f of b minus f of a over b minus a. And what is f prime of c equal to? Well, f prime of x is 2x, so f prime of c ought to just be 2c. And what's f of 2?
4,
4.
And f of 0?
0.
Over 2 minus 0 gives us c equals
1.
1. So that's the location where the slope of the tangent line is equal to the slope of the secant line through those 2 points. And just for the heck of it, let's pull up Desmos and take a look. Maybe. Desmos.
What a nice even number.
Wasn't it nice? I know. So there's x squared. And if we're trying to write the equation of the line that goes through the points 0, 0, and 2, 4, well, what's the slope of that line? It should have a rise of 4 and a run of 2. It should have a slope of 2, right? We found that out. So using point slope form, that should be y minus 0 equals 2 times x minus 0. So it's just y equals 2x, right? And then if we were to do it through the point 1, 1, with a slope of 2, that should be y minus 1 equals 2 times x minus 1. And we can see that clearly we know they're parallel because they both have a slope of 2. And clearly it's tangent to the point 1, 1. And clearly that one goes through both points at 0 and 2. Good or no?
Yeah.
Spectacular. Any questions on that?
Why is this useful?
Well, good question. So I'm gonna only sort of half give you an answer on that right now.
Okay.
It is useful. There are some applications of the mean value theorem. One of them is a corollary to it, which is called Rolle's theorem, which helps us to find places or helps us to find locations at which the derivative of a function is equal to 0. So places where we have local maxima and minima, and then there's applications of that also. But there are other applications of it in some higher math classes, and there are some other applications that are just like some random sort of real world situations, sort of not real world situations that it does pop up. I'll pull a few of those random real world situations that are sort of real world situations and show you guys to them. Not today because I don't have them ready, but there are some instances where it could matter. It's not a real great answer for you.
Okay.
Mostly it's used in conjunction with Rolle's theorem to help us find where we have places where the derivative is equal to 0. And we're going to talk about that a little bit today.
Okay, thank you.
Yeah, sorry, I know a lot of this seems, and unfortunately, a lot of the answers I give for like, why is this important? And a lot of the answers I give in calc is like, well, it's important because when you take this class that's 5 math classes after this one, you need to use it over and over and over again to do this really cool thing. And none of it would make any real legitimate sense to any of you right now because you're not 5 math classes ahead of where you are currently.
All right, thank you.
Yeah, sorry, it's not the best answer, but. All right, so I would like you all to take a minute here and figure out why each of these two functions fails to satisfy the hypotheses of the mean value theorem for the specific interval from -1 to 2. So take just a minute and see if you can come up with a reason why they fail to satisfy the hypotheses and why we wouldn't bother to use the mean value theorem on these. So for the first one, why does this fail to satisfy the hypotheses of the mean value theorem?
It's not differentiable.
Yeah, so if we try to find f prime of x, what do we end up with? The square root of x squared is 1 over 2 square roots of x squared times the derivative of the x squared, which is 2x. And having an x squared in this denominator means that x cannot equal 0, right? And so if x can't equal 0 in my derivative, well, then that pretty much solidifies that it's not differentiable there. And what about the other one?
It's not continuous.
Right, it's not continuous, right? If we look at the limit as x approaches 1 from the left of f of x, that's 1 cubed plus 3, or 4. And the limit as x approaches 1 from the right of f of x, well, that's 1 squared plus 1, or 2. And so if the limits from the left and the right are not continuous, then, or are not equal to each other, then it's not continuous at x equals 1. Right, so everybody good with that?
Yeah.
Okay. All right, so let's take a look at this. Let's see if we can find a tangent to this function f on the interval -1 to 1 that's parallel to the secant AB with a equal to -1, 0 and b equal to 1, 0. Thoughts on how we're going to do that?
See if it's continuous on the interval.
All right, yeah, so is this continuous from -1 to 1? Can I plug in any value between -1 and 1 in here?
Yep.
Yes.
All right, it's continuous on -1 to 1. Right, it's just the square root of a polynomial. And as long as that polynomial is defined and is never negative, right, that polynomial is always greater than or equal to 0 on that interval, then that square root shouldn't affect anything, right? As long as it's not ever negative, which it never is. And then what about differentiable? What's f prime of x? 1 over 2 root 1 minus x squared times -2x. And the only place where this is undefined would be values that are greater than 1 or less than -1. Right? So this is defined on -1 to 1. What does this graph look like? Anybody know? You should know what this graph looks like, I hope. No, nobody? Y equals the square root of 1 minus x squared. Square both sides. What does this graph look like?
An ellipse?
No.
Half of a parabola on its side.
No.
circle.
Oh,
It's half of a circle, right? Positive square root of 1 minus x squared is the upper half of a circle with a radius of 1 centered at the origin. And the negative square root would be a lower half. So we should know that this looks like a semicircle, right? So let's figure this out. F prime of C, what's F prime of C? It's negative 2C over 2 root 1 minus C squared. And we want that to equal the average rate of change. So what's the average rate of change? It's F of 1 minus F of negative 1 over 1 minus negative 1. So we got negative 2C over 2 root 1 minus C squared needs to equal, well, what's F of 1?
Yeah.
0. And what's F of negative 1?
0.
0 over 2. So we've got negative 2C over 2 root 1 minus C squared equals 0. Well, in order for that to equal 0, just the numerator needs to equal 0, or C needs to equal 0. So it occurs at C equals 0. And if I plug in 0 to my equation, what's F of 0?
1.
1. And so we know that the slope is 0, and it needs to go through the point 0, 1. Well, that would just be the line y equals 1, just the horizontal line. Everybody good with that?
So that C value gave you the slope or whatever, and then you plug that back in to find a point. Is that what you did?
No, the C value gave me the X value.
Okay, and then you plug that in.
At which I plugged it in, yeah.
Okay.
So here's 1 minus x squared. There's your semicircle. And y equals 1, tangent to it, and clearly that's parallel to the one that goes through the points 1, 0, and negative 1, 0. All right. Yeah, so we went through and we found C equals 0. C equals 0 tells us the x value at which this parallel line occurs, and then we plugged 0 in here to find the actual point 0, 1. Any questions or issues on that?
How'd you find the slope? Where was that? Or
Okay, so we knew that the slope had to be the same as this slope was.
oh, so okay, I see. Yeah.
Right, and that slope was 0, right, because they're parallel to each other. Alternatively, we could just take 0 and plug it into our derivative, but we already knew that value. So if we plug 0 into our derivative, we get 0 also. All right. So now, lastly here is Rolle's theorem. So Rolle's theorem is just a corollary to this mean value theorem. And it says that all the same stuff, if it's continuous on the closed interval a to b and differentiable on the open interval a to b, and if f of a is equal to f of b, then f prime of c has to equal 0 for at least one number on a to b. And that's effectively what we had here, right? We had f of a was 0 and f of b was 0. F of a and f of b equaled each other, which meant that there had to be one place where the derivative was equal to 0, one turning point or one potential turning point, one place where there may be a min or a max of this function on that interval. So that's what Rolle's theorem is saying. Rolle's theorem is just the mean value theorem, but where f of a and f of b are equal to each other. Good or no?
Yeah.
All right, so let's see if we can use Rolle's theorem to figure out if there's a place on the interval 1 to 4 where the derivative equals 0. So first off, is f continuous on 1 to 4?
Yes.
It's polynomial. And what about f prime? Does it exist on the open interval 1 to 4?
Yeah.
Yep, because it's a polynomial also. Right. What's f prime? F prime of x is equal to 8x minus 20. Yeah. And then we also need to figure out what's f of 4 and what's f of 1, and do they equal each other? So what's f of 4 equal to? Should be what, 64 minus 80 plus 29?
13.
13, it looks like, right? And what about f of 1? 4 minus 20 plus 29, also 13. So f of a is equal to f of b, which tells us that f prime of c, which is 8c minus 20, had better equal 0 somewhere on that interval. Well, that happens at c equals 20 over 8 or 5 over 2. Good or no?
Yeah.
All right. That's it. That's the mean value theorem for derivatives. At this moment, it probably doesn't seem super useful, but it is.